Damn.
Okay, recording in progress. Roger's not going to be here today, so make sure that I remember to record. Okay, good morning. It's February 8th, 2026. This is the Cosmology discussion group. My name is Harry Ricker, and this morning we're going to have Ian Cowan talk to us about I forgot what it was. I got so spaced out over the business of trying to sign in. So you're going to talk about electromagnetic theory, and so go ahead.
Dynamics, fluid and electrodynamics.
Right. That was the part I forgot. Apologize for that.
No problem.
Okay, next week we've got Rick scheduled to talk about the electric universe. And we don't have anything scheduled for the week after that. So that would be the 21st or the 22nd of February is open. So we don't have anything scheduled after Rick. So if you want to make a presentation, let us know. Okay, I want to mention that Vladimir is going to talk on Saturday about Hubble tension. Okay.
He doesn't seem to be here today, by the way.
Well, yeah.
So far.
All right, you can go ahead if you want to give me a request, share your.
Now, how do I do that? Share. Send request.
Okay, you can proceed.
So all I do is I put my own slides up and then proceed. Okay. Let me see now. I think I'll minimize that. Slides. I have to open them now. Thought I had them up. Here they are.
So, Bob, did you ever hear of quietism before? And
I heard of the
Roger?
philosophers he was talking about, like Wittgenstein and Mach, but I don't know if I'd heard that term before.
Yeah, that kind of like stunned me a bit.
But
Yeah,
he was
it's an
accurate
AI
about what they were
term.
saying. Wittgenstein was like that. You have to pass over things in silence. I don't particularly agree with Wittgenstein.
Well, one comment that was made in the chat was that Galileo was the originator of the quietism.
I thought it was Newton, hypothesis non fingo.
Yeah, Newton was sort of like that. A bunch of people have been sort of like that, often just because they don't have a good answer to a question. They say it's nonsensical, the question.
You having a problem, Ian?
Hey, can you not see my stuff now?
No.
No.
Really? But it's up. Okay.
Did you throw
Sorry
out the
for,
request to Harry?
I sent a request to Harry.
yeah,
Now,
I
do I need to
approved it.
share again?
I
Share.
approved it.
Okay, I didn't click on the thing, maybe.
You have to click on your file. There you go.
There you go.
Okay.
Now you're working. We were basically chit-chatting away while we are waiting, and that probably
Yeah, and I was assuming that you'd see them and you were just chit-chatting.
right.
Now, I noticed the last time, even though one makes the slide show, it's still impinged at the right-hand side by the videos. Certainly, let me see now.
Well, you can go up top. There's this view on the top bar, and you can move the videos to the side. Okay, well, this looks pretty good.
I think I can even do it physically, but I wish I could get. There we are. I think I've more or less done it.
All right, I think we're ready.
Okay. I can actually get rid of them altogether. There you are. Okay. Right. Well, thank you very much for inviting me. I suppose I did volunteer, but thank you very much for accepting it.
Well, I appreciate that people want to talk, and if people don't talk, we don't present. We run out of subjects to talk about.
Of course.
I ain't got nothing to say.
Sorry, what was that?
I ain't got nothing to say.
Who's that speaking?
That was Rick.
Rick, okay. Ain't got you sounded US, not Canadian there. Okay, very good. Now, I have talked a bit about this subject before, but it's an extension of some of the earlier work I did, maybe dating back, oh goodness me, almost a decade. So, what I am endeavoring to do is look at the subject of dynamics. Now, I conform to one of the definitions, which is probably not the majoritarian definition. Very commonly, dynamics is taken as the study of forces on objects in motion, as distinct from statics, the study of forces on stationary objects. But another definition, and actually probably more faithful to the etymological one, because dynamos is basically the Latin for force, would be to take dynamics to cover the forces on objects, whether they're in motion or stationary. So, in other words, dynamics include statics. And to take the two elements, one dealing with objects in motion to be kinetics and statics to be the case where the objects are stationary. So in other words, when I'm dealing with dynamics, I'm dealing with statics. So things like Coulomb's law will be included. And fluid, well, I'm taking fluid to be either a gas or a liquid, and electro. And I've left a bit of a space there just to,
So
to
can I
explore.
stop you a little bit here? This
Of
sounds
course.
like the term that they use is reifying or reification. Are you reifying electromagnetism?
Am I? I've seen that term a lot.
I think it means to make it physically real. Is that correct, Robert?
Well, reify means to make something exist.
Right. And
Yeah.
so are you saying that you're going to assume that electromagnetism is a fluid? Is that what you're driving at? Or are you using the fluid as just
Yeah,
a model to describe it?
perhaps I might express it this way, that I'm endeavoring to integrate electrodynamics into other branches of classical physics, which perhaps for the last 100 years or so has appeared not to be the case. They've said, oh, this is a very special case, and we're going to have to introduce new ideas, and it cannot be dealt with in classical terms. So rather than reifying it, I might be integrating it, perhaps.
Okay, well, just
Okay. It's a good question. And please feel free to interrupt because I know it's a very conversational type of discussion. And actually, when you were discussing matters before I got my slides up, you were stealing and thundering away because my first one is, let me get the Latin pronunciation.
okay, good.
Who potaces non fingo. So I think most of you will know my method actually, because you've probably heard me before to some extent, and I'm a little voluble now and again. I have kissed the Blarney Stone on a number of occasions. Now, uh, so without appearing to be too pretentious, I hope, I might say that my method is basically the same as Newton's. I do not engage insofar as is possible in formulating hypotheses and then advocating for funding or advocating for other people to do those experiments to see whether all those myriad hypotheses are correct or not. And similarly, I do not start plugging things into AI and just getting all the answers out and speaking ad nauseum about that. What I do, we are dealing with an experimental science, so I get some basic exact experiments, and I try to formulate a mathematical theory based on those or a mathematical model based on those. And then that's sort of like the inductive process. And then I use that model for deduction to predict certain events. And then I test whether those events actually do come to pass. So just to remind you, gentlemen, I'm sure you're all familiar with this, the exact quotation from the Principia is, he says, hitherto we have explained the phenomena of the heavens and of our sea by the power of gravity, he's talking about gravity, but have not yet assigned the cause of this power. I have not been able to discover the cause of those properties of gravity from phenomena, and I frame no hypotheses. Hypotheses says non fingo. For whatever is not deduced from the phenomena is to be called an hypothesis. And hypotheses, whether metaphysical or physical, whether of occult qualities or mechanical, have no place in experimental philosophy. So I'm not making myself out to be perfect, but I don't like to get involved in these never-ending email to and fro's about, this is what it might be that, and it might be this, and the real world is something like this. Maybe actually to take from the earlier discussion, I might be engaging in a little quietism here because because I'm saying, look, this is what the mathematical equations based on theory connote, but I'm not going any further. I'm not saying that they're real. They're perhaps the atoms, going into the atoms, saying exactly what's happening here and there, or even in the ether, saying what's exactly the ether is composed of, and so on, is maybe going a bit too far. So, as I say, if I'm not being too pretentious, I am taking a leaf out of Sir Isaac's book.
Okay, let me kind of interrupt
Yeah.
a little bit here. I think this is an important point. And I was kind of surprised by the this quietism thing because I'd never heard of it. But I thought that people referred to this as the empiricist philosophical approach in quantum mechanics. Are you familiar with this, Robert?
Yeah, well, I mean, sometimes called like positivism or with the Copenhagen interpretation of quantum mechanics. Yeah, where you just say you're just dealing with observables, and maybe people when they try to go beyond that, sometimes they say it's meaningless and things. So they don't all say the same thing, but was a tradition like people like A.J. Ayer that would say if you can't verify it, then it's meaningless.
Yeah, this seems to be kind of an issue that is being discussed in the scientific community, but I think the terminology that's being used, positivism, empiricism, quietism, I think that's confusing. I think there's a different terminology is being used, and it's not really clear what they're talking about. But I think the origin of it is this hypothesis non fingo statement that we have here on the screen.
Mhm.
Can
And
I
for my
can I
part,
ask
I
a
might
question?
say, no, go ahead, Jim.
Um, the first sentence here seems to me to be a contradiction. Of course, I'm probably wrong, but he says the power of gravity, but have not yet assigned the cause of this power. Well, in his universal gravitation law, he does assign the cause of the power as being mass of the objects in kilograms. So it seems to me, was this statement written before his postulation of the universal gravity law?
No, I would say he's talking here about the ultimate cause. Uh,
The ultimate
yeah,
cause, like
ultimate
like
reality.
like what causes mass in his equation?
No, just say mass is a parameter which is a numerical quantity which goes into the equations and can therefore determine the force of gravity and so on. But what is the cause? Is it a
Well, what if
spirit?
the cause is not mass, whether in its form as a numerical quantity or otherwise?
I
Yeah.
think we're perhaps using cause in two different
Well, also, you might
meanings.
distinguish between a distal cause and a proximate cause. He's definitely not making a hypothesis about the proximate cause that's adjacent to the effect. But you're right, Jim. He is talking about mass, but that would be the distal cause at a distance.
Okay, I just wanted to point out that at least for some people, like little people like me, that sentence seems to be a contradictory. At any rate, please proceed, sir, Ian.
Okay, I'll do it. So anyway, that's really an introduction, but I'm delighted that it spurred on some of this conversation.
Well, I think this is an issue about what science is about and what science is trying to accomplish. And I think what he's meaning there is that gravity, a lot of people wanted gravity to have some kind of physical phenomenon. So, for instance, at this time, the mechanical philosophy was in vogue. And so, if you go back to that slide there, I think what he's saying is he doesn't have a mechanical cause. In other words, there's no
Yeah,
he
Yeah,
doesn't
unlike the Fatio or Lesage would be a mechanical cause.
right. So there's
right.
not a physical operational cause that he's not speculating on a mechanical cause for gravity. It's he's just made his, yeah, and this is kind of
Well,
it's a mathematical operational description of how gravity works. He doesn't explain gravity, he describes how it works.
Yeah, that's
right.
another way of saying what I was trying to say. I agree
Well,
with you.
in simple terms, it's a question of whether or not a, a, a a kilogram has uh, gravity intrinsic to it. But the thing is, we don't know why this kilogram has this gravity power to it. In the electric universe, we think it's all the atoms are positive, are pointing inward, and all the negative atoms are pointing outward, and that's gravity in the electric universe terms. So if in simply, it's just an electric charge, basically, in my view.
Well, to deal with the proximate case that I'll be coming to shortly, namely the ether, I shall be attempting to ascribe properties to that and quantities which will determine how it behaves. But I shall refrain from delving into what it actually is, what it is composed of.
Right. And that's what the question was uh, what is gravity? We know gravity is associated with the kilogram. It has a certain gravitational pull to it. But what causes that? Nobody knows. Nobody
Well,
knows.
that's what Newton's saying here in this first
Yeah,
slide.
exactly. And I mean, if even though he's attributed it to a kilogram has a certain potential, then but we still don't know what that cause is.
In another part of his writings, he veered into a sort of theological, which is probably a bit dangerous, but he said, since we do not know the ultimate cause, it would require a divine hand to impress gravity upon matter. He said that somewhere else. Anyway.
Okay, next
Well,
slide.
it's very curious that in his second sentence here, I have not been able to discover it's gone.
Sorry,
I
I've
have
put it
not been
back
able to
in.
discover the cause of those properties of gravity from phenomena. Well, prior to his work, mass had been excluded as a cause of the observed properties of gravity, as I pointed out in previous presentations. Yeah, anyway, seems to be that Newton is going around in circles here. That's all I have to say on that matter.
Yeah, this is a
Second, yeah.
fundamental issue in science. They've settled on description of phenomenon rather than causes of phenomenon. And that sort of led to this quietism.
Or they've assigned the wrong causes.
Well, that could be. Yes, that's another
Well,
problem.
prior to Newton, mass was excluded as a cause of gravity. It was not even included. Gravity was defined as an acceleration, and mass does not appear in the equation or expression, mathematical expression for acceleration, And furthermore, experimental observations, the so-called Tower of Pisa, dropping two objects of different masses, and they arrive at and they accelerate equally, had excluded mass as a cause, and yet Newton trotted out that mass essentially is the cause of the force.
Well, with respect, this is all most interesting, but it is not really very central to what I'll be talking about today.
All right.
This was merely to indicate my methods. We should perhaps have a talk on this maybe on the 15th of February or whatever, 22nd of February.
All right.
But you know, we perhaps should move on, Harry, because it's not
Right.
really germane to what I'll be talking about.
Agreed. Let's move on.
Okay, go this way.
Now we're going backwards.
Okay. Well, I've just put four references here because James Clerk Maxwell, Volume 2, Chapter 20, Electromagnetic Theory of Light. I'm dealing with that. Now, what I'll be doing today, actually, although I talked about fluids generally, I shall be taking a specific example with regard to longitudinal compression waves, namely sound in air. And I've taken Lord Rayleigh's Volume 2, The Theory of Sound. So there, it's actually particularly Article 246, which is the general dissipation of sound. And I also refer to two papers, one which I talked about on a previous occasion, this Italian man, physicist, who's still alive, I believe. I think, anyway, he's quite elderly, named Monti. He gave me a lot of ideas early on in the 1990s, his critical analysis of the theory of relativity, where he introduces such things as the conductivity of the ether. But see, Maxwell does as well. So Maxwell has a term C, not current, it's the conductivity of the ether. And then he says if C equals 0, you get these following tests. So they've deleted that C term, but Maxwell has it in. Monty calls it sigma naught, which I do as well. And my own paper later on in 2018 on the analogy of electromagnetic waves. Is it an anomaly or is it an analogy? And I've given a presentation on that before. So we can deal with those further. Now, just to remind you all, I know we've talked about this a lot. And I'm concentrating on the fact that these mathematical theories that I shall be describing have been developed from experiments. Now, in the case of Maxwell, mainly from Faraday's detailed experiments, but also from those of Gauss and Ampere, who did experiments as well as being analysts. Now, in the case of Rayleigh, which I'll be dealing with the sound, he's got these two volumes, monumental volumes, quite mathematical. Basically, there isn't a sort of Faraday, John the Baptist there, but he came to his conclusions, and he quotes a lot from earlier experiments with musical instruments. That's been going on for a long, long time, hundreds and hundreds of years. Vibrating strings, air columns, resonators, and more recently by the work of Helmholtz, the German physicist, and practical organ builders, etc., etc. So a lot of information had been built up, and it just required to quantify it. Because it was actually Kelvin who said that when we get some results, we know very little about the results until we actually can quantify them. So quantifying the results in everyday parlance would be sort of putting arithmetical numbers on them. But in the more mathematical terminology, it would mean formulating a mathematical theory or a mathematical model which would encompass all that and then can be used to deduce further results. Okay, so shall I go on now? I can always go back if you have a question. Now, what I've done here, and I've actually generalized this from the last time I presented it. I say any fluid can be conceived of as an infinite transmission line. So we're talking in terms of electricity. You can have an inductor element here, which will store the energy because you have a current going through that, and you have voltages here in the ladder, and then you have a capacitor, if you like, can discharge it down to earth here. But this is quite general. Now, so in an ideal situation, you would just have I suppose in the electrical terms, you'd have a magnetic store. Where's my cursor gone? An electrostatic discharge. I'm just trying. Here it is. But in the general case, you'll actually have a little resistance there, which we might call R. I haven't put it in. And you'll have a little conductance here, which we might call G. So the resistance here will be very small, and it will result in loss. So in other words, the voltage will be decreased, Vn minus 1 to Vn. But you'll also have a conductance here, which will allow some current to discharge further. So we can call that leakage. And I'll be giving the general equations for those because they're a bit complex. But in the general electromagnetic case, the R value is very, very, very small. It's vanishingly small. But the G value is not. So we'll come back to that later. But the general equation for the speed of transmission through this line would be that, where L is the inductance per unit length and C is the capacitance per unit length. Now, I'll be talking about the analogs for that in the mechanical sense, because what we're doing is we're analyzing a fluid by the various equations, by the Navier-Stokes equations and so on. And in particular, we're looking at it from the Eulerian point of view, where we're looking at a position of the fluid as it's moving. And we're seeing how things like pressure, density, and velocity change at that point of our interest. Okay.
Can I ask a question here?
Of course.
This equation C equals 1 divided by the root of LC.
Yes.
What is the origin of that equation?
Okay. Well, first of all, there is an equation which actually is called Thomson's equation because it was developed by Kelvin before he was introduced to the peerage. He was made a lord. But Thomson's equation is omega, which the angular frequency is equal to 1 over twice pi squared of LC. Now, this can be derived quite simply. I could do it if you really wanted to, could do it now, but it's actually in my paper. So in other words, if you just work out the equations here, you get basically the current relating to the change in voltage with respect to time, and the voltage relating to the change in current and the change in time. So in the case of an inductor, it's di by dt, L di by dt. You get that voltage difference. And in the case of the capacitor, it's I is proportional with C times dl dv by dt. Now, if you take these as being discrete elements, you can get Vn minus Vn. You can get the difference there, and you can get the difference here, and so on. Now, if you get two equations, I can actually show this to you if you wish. It's in my paper. And if you divide them out, you get that the impedance is equal to the square root of L over C. And the speed of transmission is equal to 1 over the square root of LC. So they're quite simple equations.
1 over the impedance, in other words.
No, not quite. No, the impedance is the square root of L over C.
Oh, excuse me.
Okay.
Okay, well, I was just interested in the origin of that equation.
I can
That's not
get
your
it.
central topic for today.
Yeah, it's
so
not.
I
It's
don't
not.
want
It's
to
not.
divert you.
Yeah. Yeah. No, you're asking good questions, and I can keep on saying it's not the central topic, and you're kind enough to agree all these things, but they're interesting. But we can come back to them if absolutely necessary, and I've no problem in your asking them. I actually wish you asked them, even if they're extraneous. But it's a simple derivation anyway, and I can get it for you later if you're
Thank you.
There's a fundamental equation of electromagnetism right here. These
Yeah, I
two
mean, Harry wouldn't
equations
even
that you
ask
just
that. It's
mentioned.
just we wouldn't even think about it. We say, "Oh, that's it." The important thing, by the way, is L is frequently used for inductance, saying Henry's, C capacitance and farads, but it's actually inductance per square per unit.
Right.
So, in other words, Henry's per meter and capacitance is farads per meter, and that's important in a way because when we start looking at the ether, we don't have a fixed distance, and we talk about epsilon naught and mu naught. So epsilon naught would be the analog of L here, and mu naught would be the, sorry, beg your pardon. Mu naught is the analog of L, and epsilon naught is the analog of C. Okay,
Thank you.
you're
All
very
right,
welcome.
we got like 6 minutes.
Oh, well,
Keep
tell me when to
going.
stop. I can go to the
Keep
next one if you
going.
want. Okay, I'll keep going. Now, sorry, it's a bit getting a bit difficult now, but basically, if we explained in some terms, general wave equation with dissipation for anything. So if you forget about these two terms here, that's the wave equation. U is a function of x and t. Now, for example, in the case of a fluid, it could be, what have I done? It could be the variation in pressure about a steady state. We're not talking about absolute pressure because you have a static pressure, but the variation on the pressure, or similarly, the variation in the density. It could also be the velocity gradient. So sorry, the yes, the velocity gradient. Yeah. Grad V. In the electromagnetic case, it could be the electric field strength or the magnetic field strength, E or H. But if you neglect the second two terms, you get the commonly known wave equation, where the second differential, partial differential with respect to the we're just taking it in the x direction, so it's a planar wave to save complications. We don't bring things like nabla in there, but you can do it without. This is without loss of generality. Y and Z, it's moving the x direction. So with respect to the dimension, is equal to 1 over c squared times the second differential with respect to time. So that's the well-known wave equation. But for generality, there's a dissipation which is proportional to the rate of change, not the second rate of change, the rate of change of the variable times k, which is a dissipation constant. And there could, in the very general case, there could be another one which is proportional to the value itself times gamma. Now that's actually very, very small. We'll see that in a moment. So gamma's normally zero, but just for generality. So you know when you talk about a body falling from an airplane or something, the resistance of the air impedes it. So gravity is acting upon it and is bringing it according to the general kinematic laws. But you have a resistive force, which might be proportional to the force itself, or it might be proportional to the square of it. Anyway, here you have a dissipation, which is this second term is the most important one. Now, the solution to this equation is not just a simple unattenuated wave. It's a damped component of harmonic motion, which is the normal wave solution with sine and cos terms in x and t. And if you solve that, it's quite a simple thing. You can work it out. You can even get AI to solve these equations for you nowadays. You get the dissipation factor is the exponential of that minus kt over 2. That's dissipation there. You have to multiply the cosine or sine terms by this dissipation factor. And if you take in terms of x, it'll be that x equals ct. So it turns out, and if you look at the reference I gave to Rayleigh's book, you know this actually. The first one, you know that we keep the term c celerity from the Latin for speed. The celerity is equal to the square root of kappa over rho. Now kappa is the bulk modulus of the fluid. In this case, air. In air, it's actually the adiabatic constant gamma times the pressure over rho. So that's well known. You get 1100 feet per second. We can work that out in normal air at STP and so on. Now, this is less well known. K, according to the equations which are solved, it turns out to be that. Um, it's four times nu is the kinematic viscosity. So obviously in air, viscosity is important in damping the thing out. And here is the angular frequency of the wave, twice pi f, and we divide by 3 c squared. And certainly in the analysis that Raleigh does, gamma would be practically zero. So that's for normal sound waves. Now for EM waves, again, some of this is well known. We've said that C is equal to 1 over square root of LC. Now K turns out to be G over C. So the parallel conductance divided by the capacitance plus the series resistance over L, R over L. And gamma actually turns out to be that GR over LC, which actually turns out to be exceedingly small, particularly for high frequencies. We'll come to that in a moment. In high frequencies, actually, it's the GC which predominates, not the RL.
Okay,
So
we got a minute.
yeah, okay. I better stop there, had I, Harry? And
Okay, does anybody have, this is a general wave equation.
right.
This is a very generalized, it applies to sound, waves in sound, electromagnetic waves, waves in solids, I would think, right?
Yes, yes, quite so. Yeah.
Um, so we have here a general wave equation.
And they apply to shear waves, longitudinal or transverse. So, for example, we're talking about EM waves, which are transverse, unless you're Franklin Who, but
Yeah.
although I say there are longitudinal waves as well, but that's another matter. Or we're dealing with longitudinal waves in, the sound, or in a solid, it could be a combination of both, or water. It could be shear waves, or it could be longitudinal as well. So that's correct. Yeah.
All
Earth.
right, so we got a couple of
Sideways.
seconds here. Um,
So I'll have to, when I said start again, I don't know, I was cut off there, but I just meant that I presumably have to start sending a request as well. It won't carry forward, Harry, will it?
I'm not sure. I think
Well, try
sometimes
it.
it remembers. Give it a try.
We'll give it a try. Can you see that?
No.
I
It's
don't
not
think
doing
so.
anything. So give me a share request and see what
Right.
happens.
Okay. I think I know what to do this time.
All right.
So you've
Then
done
you
it.
click on your file.
Yeah, see, I have to click, it's not just a question of clicking on the file, I have to click on share again and click on the rectangle and then click on the file.
Right.
Okay.
Right.
So you can probably see it now.
Yeah.
Okay. So all I do is I maximize it and I'm going to bring those things off to the side. Although I have a feeling that the recording doesn't do that. Anyway, we'll see later. Okay. Yeah. So yeah, that's right. The general equation which applies to all. Um, See, the one-liner,
Now you don't
would,
give the impedances, you don't give the equations for impedances. You give the equation C for velocity,
yeah.
and you give the equations for the loss or the attenuation. Okay, but you don't give the impedance, which I guess is not in a, I guess what I'm saying is that's crucial in electromagnetic theory, but not so much in sound waves.
Yeah, that's a good point. I deal with it in my earlier paper on the analogy. No, actually, I'm not wrong. It's coming in later. I actually didn't call it an impedance. I called it instead of calling it Z naught, I call it R naught, I think. So it does come in. I just haven't put it down here. But
Okay, let's move on to the next slide. If
I just want to give you well, I lost my train of thought. Yeah, the one liner as to why which you won't be surprised, gentlemen, as to why EM is an anomaly is Oh, we better tell you now. We're the experts. We're the high priests. All waves transmitted in air or in a gas or in a liquid or in a solid need a medium. But hey presto, EM has no medium. That's why it's different. Okay, that's what the mainstream say. So I'm
Well, I see where you're going with this.
yeah, yeah.
Um, yeah,
So I'm saying there is a medium, and I'm going to give
there's
you
a
properties of
different
that
other
medium.
another difference though, Ian, I think, which is that you need two wave equations for EM, one for magnetism and one for electricity, um,
Yeah.
as opposed to the one equation for like sound waves.
Don't you mean the
Yes.
electromagnetic field as opposed to the magnetic field?
That's what I said.
They
Well,
have to
you
be
said
combined.
electricity, that's current. That's different than the electric
No,
field.
electric field is okay. Well, we're going to
So
argue
I'll
about
be
what we
coming to
mean.
that, and yeah, it's a very good point. I claim it's quite simple because you have the same equation for E as for H, and when you combine them by cross multiplication, by pointing vectors and so on, you just get twice the value. I'll come to that in a moment, but it's a good point.
What
So
is
Okay,
H?
H is the magnetic field intensity in amps per meter using the SI unit, and
Okay,
E is the electric field intensity in volts per meter using SI units. Okay. So if you multiply the two together, you get watts per square meter, which is power per square meter. Now, and yeah, maybe this was what was annoying me. I've got a bit at the top which hasn't disappeared. I don't know if you can see this. I have a banner at the top.
yeah, you need to move it over to the side by going to the view
View.
at the top. Yeah, if you go to the top near the right hand side, it says view, and you can move
It says
the
more. Disable annotation, hide names of annotation, hide video panel. Maybe that's it. Yeah, it's work. All it says you are now sharing, but it's only a tiny little thing. I can live with that.
can you
Uh,
see the slide now? That's we see it fine without
you
any
see it fine.
problem.
It was obscuring me, but I can see it fine now.
Okay, let's
So
go.
if I'm reading the same as you, I've put in italics the first word, universal. Universal independence of transmission speed of emitter motion. So here I'm being a little controversial now, and I'm just coming all of a sudden to Einstein's SRT paper of 1905 on the electrodynamics of moving bodies. And I'm quoting from page one, actually. He's dealt with his first uh, proposition, his first postulate about, well, he's saying that the same laws of mechanics should apply in the case of optics and electro dynamics, irrespective of the frame of reference, inertial frames, I think he might have mentioned. But he says, then he goes on, he says, and also introduce another postulate which is only apparently irreconcilable with the former, namely that the emphasis is mine, the yellow, that light is always propagated in empty space with a definite velocity c, which is independent of the state of motion of the emitting body. I think the precision we have in English between velocity and speed doesn't exist in German, so that's why velocity is used the whole time. Now, but I say that light could be replaced with the words any wave. You see, any wave is always propagated in empty space with a definite velocity c, which is independent of the state of motion of the emitting body. That's the definition of having a medium there. So here's my
I think you
difficult.
need to worry about empty space though.
I don't need to worry about it, or you do.
Well, how is a sound wave going to propagate in empty space?
A sound wave propagates in air or in a gas with a definite speed. So, in other words, if you have a police car siren um, going through the air, and the police car is going 60 miles an hour, the speed at any instant will be emitted in the same way as if the car was stationary. And that's in a medium, air. Now, the same thing applies to light. And Mr. Einstein is making a big thing of it here. He says light is always propagated with definite velocity, independent of the state of motion of the emitting body. Yeah, I say yes, because it's being propagated in a medium, which we can call the ether, if you like. So I'm being a bit controversial here. I'm saying light can be replaced with any wave. And the second postulate, I actually like the word osios, which actually comes from the Latin. It means to be lazy or to be ineffectual. The OED, the Oxford English Dictionary, defines osios as serving no practical purpose or result. So I say, a bit controversially, that Einstein's second postulate is osios. It serves no practical purpose or result.
I would suggest that he's forced to state that because of his first postulate.
I'm sorry, is that Jim speaking?
Yeah, that was me.
I thought so. I got the voice right, yeah, because you've come in since I saw the videos. I'm pretty good at voices now, it sounds. It didn't seem like Jim, James Morrison. Yeah, it's Jim Morrison. It's not James Keane. Yeah, I think you're probably right. And in fact, Jim, he said it's only apparently irreconcilable with the former one. But why does he need to mention it? Because it's true. If he said, by the way, light
If there's no medium, then you have to make it up.
If there were no medium, the ballistic theory of Ritz would probably be correct, actually. It would be like a cannonball, where if the trolley on which the cannonball is running, it's running on a railway track, and then it emits a cannonball, you get the sum of the two speeds. But if something relies upon its velocity on waving of a medium, well, then it's independent of what velocity the actual emitting body is.
Yeah, it's trivial.
Exactly. That's all I'm saying. You got the point. And you see, people don't get this point, I think, Jim, because first of all, they mix up the emitting body with the observing body. And because of this relativistic symmetry, they say, well, it's in the speed of light is independent of how the observer is traveling towards or away from the body. Now that is absurd. You see, I've said that this is trivial, but the other point is absurd. To say that it doesn't depend on the speed of the observer is absurd. And then they start making just statements, which we're talking, all of us, we're all guilty of this. We're saying the speed of light is invariant. What does that mean? You know, we have to be very precise. Do you mean that it obtains a definite velocity, a definite speed, which is independent of the state of motion of the emitting body? That's true. Or does it mean it obtains a speed which the observer will not see changing, independent of his motion? That is absurd, as O'Rahilly and others have actually said. He said it not only seems like nonsense, it actually is nonsense.
Well, you've kind of hit upon, I didn't see, if you go to Roger's series of videos about Einstein's myths and mistakes, I don't think this is brought up. But to me, this is a headline issue. He starts off with this postulate here, which is really basically just a classical postulate of light moving in a medium. The velocity is independent of the source. So this is essentially saying that he agrees with the medium idea of defining light velocity. And then later in the second postulate, he tells you, no, I disagree with that. And
yes.
And so what is it? So generally, I think there's a contradiction here. And
so do I. Yes.
So that's really basically your point, I think.
Well, Einstein was achieving his objective, which was to cause confusion in the scientific community. That was the objective. I think you're missing the objective. So I think we can pat Einstein on the back that he did a great job in causing confusion.
I'm not sure that he was intending to do that. I think he was just basically
he was trying to explain MMX. and
Well, if he was,
his had an
I don't
obsession.
really agree with I don't really agree with that, Jim, because he doesn't really say that in his 1905 paper. So it's
I disagree with that. I think he clearly states it when he talks
where
about the
does he
two
say
ways.
anything
When
about
he talks about
MMX in the 1905 paper? It's
when he
not in
talks
there.
when he talks about the two-way speed of light, he's
Well,
effectively referring to it.
so now we're having a discussion because we're confused because
Well,
Einstein basically made this mess.
I think he was
Well,
also obsessed with symmetry.
yeah, the symmetry is a big thing because that forces him to say that it doesn't matter whether the emitter or the observer moves, you get exactly the same. But I'm quite prepared to say, and I do say it, I say it regularly, that in his initial introduction, some people call this the first one, say I call it the second postulate. The second postulate of Einstein is correct. It's 100% correct. It's quite right. No mess there at all. But it's
Why?
trivial. It's trivial.
Why? What
Well,
do you?
why? Because there's a medium there. Yeah, certainly. That's the why. I'm saying, as expressed in those words which I've quoted here, that is correct. Light is always propagated in empty space with a definite speed, I would say, which is independent of the state of the motion of the emitting body. And all classical physicists will agree with that.
With respect to the medium, which is the problem.
Correct.
Yeah.
He gets rid of the medium and replaces it with frames of reference. That's
Yeah.
the whole point. The
Yeah.
whole point is that the medium becomes replaced by the abstraction of frame of reference.
And it's incorrect. And it's incorrect when the receiver is moving with respect to the medium for
Correct.
first order at least.
and
But you,
also Einstein was, excuse me, Jim, and also Einstein was wrong in terms of talking about empty space, and there is no empty space.
Well, that's another issue.
Yeah, the vacuum. Mm.
So he would claim he sort of waffles on that by saying ether is superfluous or
Yeah.
not needed.
yeah, but it's
So
worse than that. His first postulate essentially says it can't be true. It's
well, the first postulate is the principle of relativity, if I'm not mistaken,
Yeah, that's what I take as well.
and that's where the reification. That's where he makes reference frames to be the medium.
without being a medium.
Right, exactly.
And if there is a medium, it does not. The first postulate it would be wrong because the
Yeah, well, this is
medium
where
is
the
separate.
argument is.
Is separate from from kinematics.
Well, that's philosophical. You're right there, but it's a philosophical discussion because you
Yeah, I'm
might
sorry if I
equally say,
sidetracked things.
no, it's fine. It's fine to say it. By the way, I have 14 slides. I'm on 7, so I'm halfway through. So I better go into more. But it depends how you say it because you could put it this way. You could say, uh, if there were no medium in normal dynamics, in other words, if there were no air, say, then Newton's first law would be correct. But since there's air, it's incorrect. Well, we don't say that. We just say that air will give you a frame of reference. So in other words, if you're traveling through air, the air will, first of all, it will impede you. So the object will not continue in a state of motion forever. And also it'll give you a frame of reference between an object which is stationary and an object which is moving. So air in that case is the mean. But we don't normally say, well, Newton's first law is incorrect because there's air. We say it's an idealization. Now, if there were no ether, yeah, I suppose there would be no frame. But ether bears the same relationship to a wave because if there were no ether, there'd be no wave, as air does to sound, because if there were no air, there'd be no sound. So it's philosophical, really. But we're all in agreement, but we're expressing our views in different ways, I would say.
Well, we're back to the hypothesis non-fingo problem, which is we're not really discussing reality of what the physical causes are. We're just making mathematical descriptions.
Yes.
And Einstein is essentially saying my description, mathematical description, is applicable in different frames of reference as if they were different mediums. Does that make sense?
Or as if there were no universal medium.
Wave propagation and kinematic behavior are separate categories. And Einstein tried to merge them.
And
Well,
one
he
might,
was
excuse me.
okay.
I'm sorry.
Let
Shall I
the
go on?
issue.
No?
Do we have the next slide, Ian?
Okay, because
I think we
that,
killed
in
this
a way,
one.
I'm delighted again. I'm not criticizing you. Delighted to have this conversation. But this slide here was a bit of an aside. I was really digging it in a bit, you know. So let's get more to the meat now. Why is it not going advancing now? That's very odd. Oh, there we go. Hit the press harder. So, so let's just deal before I go into a bit more detail in electrodynamics. Let's just take one example of sound and air. And I just want to look, you remember the damping factor? It's a bit different. There's a C cube now, and there's a 2 factor there, just to tell you why that is. You see the K value there? That's worked out by Rayleigh. Well, the damping factor uh, is K over 2C times X. So if you divide by 2C, you get 2 nu omega squared over 3C cubed. So that's what that is there. So if you plug that in, you get the diminution of amplitude of the waves varies inversely with their wavelength. So if you take a high frequency wave, 1 centimeter wavelength, sound and air at 30,000 kilohertz, the dissipation to e to the ratio of 1, so 2.71828, that factor dissipation after traveling 88 meters, which turns out to be 0.3 sound seconds. But on the other hand, for waves of 10 centimeters wavelength, which is only 3 kilohertz, the dissipation to e to the 1 is after traveling 8.8 kilometers, which is 30 sound seconds. So the higher frequency is dissipated much more rapidly. But these are values that are, you know, just obtained by ordinary physics and plugging in the numbers, okay? And nobody says that this thing goes on forever. And I'm saying, goodness me, gentlemen, I've shown you that there's such a thing as tired sound, okay? And you don't start
Oh,
shouting at me and
all
saying there's
right.
no mechanism for that. You know,
This is, let me ask you a question. This is over and above the inverse square dissipation?
that's a very good question. It is, yes, it is, because the inverse square dissipation is just the general diminution because of it spreading out, and it's basically area thing. You know, you get the sphere would be 4 pi r squared. So but this is actually the diminution of the amplitude uh, owing to the exponential function here, which
The
is on top.
damping factor. I didn't
Yeah.
know this is, I didn't know that this depended upon frequency. I didn't know this.
Yeah, yeah. And it's not obvious, actually. We'll come to the electromagnetic in a minute, but it's not obvious. I mean, it's quite complex how he works out these equations, but it seems to be all genuine. I've looked at it. And also Lamb's hydrodynamics, where he's dealing more in fluids, he has a similar equation. So, and yes, frequency comes in there. Actually, I changed it. Uh, what Rayleigh has is mu over rho there, which is the dynamic viscosity. But mu over rho is the same as nu, which is the kinematic viscosity. So actually, density comes into it as well as viscosity.
Does
But yeah.
So would this mean, Ian, that, for example, thunder from close lightning bolt would have higher frequencies that we would hear compared to a distant thunderbolt thunder.
I think you have it backwards.
Yeah, it turns into a rumble.
The higher
If
frequencies
it's
are
distant, it would be more of a rumble, as Jim says.
right.
Yeah, you can hear at close ranges, you can hear the crack of a thunderbolt and then the boom.
Okay,
When it's distant, you can only hear the boom.
okay, I understand what Ian is saying.
It's like elephants. They can communicate over great, huge distances, miles and miles, with
Yeah.
their very low frequency vibrations that they make.
Yeah,
You
that's a
can't
better way
you
of
can't
expressing it.
Yeah, you can't do that with a voice because it's a higher frequency,
That's right.
even though it might project with a larger energy
See,
than
that is indeed the essential point, because the other things you were talking about are related, but the things about, lightning being discharged quite close by, there could be an ionic dissipation or something. There are other factors which come in there. But what Rick has just said is the essential point here about lower frequency. The same thing with these sonar, I think, which is used by whales and so on in the sea. They use a low frequency means of communication. They can communicate over miles and miles, I believe.
hundreds of miles
Hundreds of
with
miles.
whales,
Right.
hundreds of
Like,
miles with
yeah.
whales, because the density of the water is far greater than the density of air,
Well, that's another
and
point.
and
Yeah.
that allows sound to travel even farther.
So your dampening factor, Ian, uh, would another example of that be the communication with submarines around the world from a central place using very low frequency EM radiation signals?
Uh,
I understand that very low frequency signals are used to communicate with submarines at
Yeah,
great distances around the world.
transmitted submarine under the water.
yeah. From satellites, they transmit a low frequency sound that penetrates deep into the water, so they can communicate with their submarines.
Okay.
Yeah.
Could
I
And
this,
think
the
we're
point
with you.
about the density is right there, because the density comes into the denominator there, and if the density is higher, that approaches a smaller number, which is almost one. So
could
there's
this
less
have
dissipation.
sorry, could this have any application to redshift, cosmological redshift?
It does. You've anticipated me. Give me two more slides, and I'll demonstrate. How did you guess? You're thinking on the same lines as I am. Yeah, yeah. That's exactly what I'm doing. I'm trying to soften you up already.
Great minds think alike, huh?
Because I told you that when I mention tired light, it's like a pejorative term. I don't speak nonsense, but I've talked about tired sound. So I'm trying to prepare you for that, and you've anticipated me, yes.
Cool.
So shall I go on? Slide 9.
Please.
Sorry, you'll be sorry now about this, but this is the most detailed slides, I think. But it's just my way of trying to express complex equations in not too many lines. What I've done in braces here, I've put either E or H. So you take the first one. So that div E equals naught in free space with no additional charge. Div H equals naught. And here, for example, this one, the Maxwell equation. Curl, take the first one, E, plus, you take the first one, mu naught, the rate of change of H with respect to, partially with respect to time, equals rho naught, minus rho naught H. You find that if you do that with the pairs in sequence, you get the four Maxwell equations. So I've just written them as two. But I've introduced two things here. Sigma naught and rho naught. Well, the reason I have sigma naught E, for example, in the second equation, well, that's just by Ohm's law. That's the That's J. That's the current density. J is equal to sigma E. You remember that equation. But I've introduced another thing which is unfamiliar. Rho naught H. So sigma naught is the conductivity in free space. Rho naught is the resistivity. So theoretically, if the Maxwell equations were to be made symmetrical, you'd have a rho naught H, which actually this is called the conduction current density, as distinct from the displacement current density. This one could be coined the obstruction voltage density, if it were to exist. But at high frequencies, it's either non-existent or practically zero. But for completion set, I've put it in because I've put sigma naught in. And remember, in the ladder network, I have both conductance and resistance. Resistance is the dissipation, is the loss, and conductance is the leakage. So for a transmission line, these are fairly. Remember the K factor, which
Ian,
yeah.
what is that plus minus symbol on the right of your second equation?
Yeah, that's a good point. There was a problem that should really be here. Actually, it's you're right to point that out. And this was put into a mathematical routine, which at the time I didn't have access to edit. So it just means that plus or minus. So for example, the first equation where you take E mu naught H rho naught, you take the minus. For the second equation, H epsilon naught E sigma naught plus.
Understood. Thank you, sir.
Okay. It's good to point that out. So here, for the transmission line, K, which is the damping factor, in the general case is that. Symbols have the meaning I've given you, which can also be expressed because C squared is 1 over epsilon naught mu naught. It can be expressed as that one. So you see that is in terms of the resistivity and the inductive storage. And here the conductivity and the capacitive leakage. And gamma is that. So this is just by solving equations. Now, at electromagnetic frequencies, as I say, this one dominates. So you can take this. This is basically true. K, you'll find this actually in advanced electrical engineering texts as well, because K is equal to the conductivity time divided by the permittivity, and gamma is equal to naught. So that's where the dissipation comes from. And I remind you that in sound, K was equal to that, and gamma is equal to naught. Okay. Now, I'm giving you a preview of maybe the next slide or two. So I just say here, just to alert you to the fact that redshift data could give you the value of sigma naught, which is the conductivity in Siemens per meter in terms of SI units of the ether. And you can find out when the energy is reduced by the factor of E to 1. So, and actually, again, my next slide will go in more details, but doing the calculations, it turns out to be about 10 gigalight years. So it's 10 to the power of 10 light years. And I just reminded you, because we did advert to the fact that it's actually the cross product of E and H, which gives you the Poynting vector, which is concerned with the energy dissipation across a surface, or by the Gauss's theorem, it's the divergence of that over a volume. So actually, in simplistic terms, it means that the dissipation factor, is E over whatever the value of the kx, so on, divided by 2, but you have that twice, so the 2 factor goes out. Well, maybe just go back. Remember here. So you have this twice. So it's E actually to the kx over c. So I'll show you that now. Here it is. Sorry. This is probably my last complex equation, actually, slide. Electromagnetic wave equation. Maxwell's equations, including conductivity, leads to a D'Alembert that does not vanish. Now, the D'Alembert is quad squared. And again, I have the braces with the E or H. It applies to both. Now, that's the wave parameter. And that if that equals zero, well, then you get a simple wave equation with no dissipation. But it doesn't equal zero. It equals, and here is your earlier question. Was it Jim or Harry mentioned the impedance? Here I call it R naught, which is, I think it was Jim, which is the square root of mu naught over epsilon naught. Well, here I have it here. Next line. There it is. That's R naught. The ether is, it's about 677 ohms, isn't it?
377.
Sorry, you're right, 377, yeah. And sigma naught there, and C naught, the -1. And the differential of that, depending upon that. So R naught is that 377, and C naught is that, which is the speed of light. Okay, it's well known.
But those are in a non-dissipative ideal vacuum, right? The C0 and the R0. They assume you don't have any leakage or dissipation or conductivity losses.
Well, they are traditionally calculated thus. But what I'm doing is I'm saying, let's take those parameters, the impedance and the...
Oh, I see. But you're using
Yeah,
those and substituting them into the equation.
yeah. And his sigma naught has come in there because remember, if there were no sigma naught, there'd be no differential with respect to time, which is coming into the wave equation. So you just have the simple wave equation. So that's where
All
sigma
right,
naught
we've got
comes in.
like
How long?
5 minutes.
Okay, well, I'll continue. I might have another slide or two. Now, I just mentioned in parentheses here that so an infinite dielectric rigidity would be if you can impose any potential difference across an area and the system will not break down because there's nothing there, there's no ether. So that would follow on from conventional views. But Trowbridge, experimental physicist based here in Dublin, actually, he measured the dielectric rigidity in 1897, and it wasn't infinite. He could actually get a breakdown. I'll give you a value for that in a moment,
Is that
actually.
in a vacuum or in air?
In very good question. I think it was in a vacuum because in air you could say the air molecules were. It's a vacuum. The vacuum dielectric rigidity. Yeah. So because otherwise it might be trivial. So the solution to the partial differential equation provides exponential dissipation in the Poynting vector E cross H. So it's that there's no factor of 2 there, and I'm actually defining RD, which is dissipation distance, which turns out to be that, because that's the factor which comes into the exponential term. 1 over R naught sigma naught. Okay. So I think we'd get away from these in a minute. Now, so what we do then is we say, well, look, galactic spectroscopic redshifts. We use the Planck's law, E equals h nu, relating energy quanta and frequency. And if we do that, the energy dissipation in the EM wave can lead to spectroscopic redshift. Just as the energy dissipation in the sound wave led to a frequency increase. Sorry, reduction, frequency reduction, redshift. And we might want to talk about this later, but I say that's better than nonsense about an expanding universe, which provides huge luminosities of these distant galaxies and very high recession speeds. And we also have things like the age of the universe, 13.8 thousand millions of years, or 1 over the current, the accepted view of the Hubble parameter is 14.4, and the 2.7 Kelvin illumination, which they say, oh, that came out of the cosmic microwave Becker radiation. But theoretical studies before that was actually measured gave values all over the place, anything from 5 Kelvin to 60 Kelvin, you know. Anyway, so this is where Monty has got, it's a bit old now because it's 1996, 30 years ago, but he got the data from the absolute magnitude and the magnitude that we have and the distance of these galaxies. And he plotted them out, assuming this exponential decay. And he got these values, these are not my values, that sigma naught would be, you know, very, very small conductivity, but non-zero, times 10 minus 29 Siemens per meter. And this gives, in my calculations, RD would be that, you know, plugging in the resistance of the ether and this conductivity would be the 10 gigalight years. And by the way, if you plug it in those values, you get the dielectric rigidity, again, in a vacuum, would be something like 4 times 10 to the power of 20 volts per meter. Hence, tired light. Tired light. Is there time to go on, or shall I stop there? How long is
We
there?
got about a minute.
Yeah, I better stop there.
I guess
11.
we could stop here. So, but these numbers that Monty is given don't really assume a cosmic medium as Vladimir would be proposing.
Yeah, that's a good question.
I mean, Vladimir has shown that there's uh, discussed that based on the measurements that there's a medium for based on the radio burst. So there's some kind of medium out there that causes the radio burst to be dispersed. And so that implies there's an actual real medium but this doesn't take any medium into account. Is that correct, or is
Well,
he
I'm not
guessing?
sure. No. I think they'd be two sides of the same coin, Harry. Now,
Well, I'm asking these calculations that Monty did. What was the? Well, we'll discuss that in the next session, I think, because we're
yeah,
going to get
yeah,
cut off here.
yeah.
So I guess that would be my question. You know, what assumptions did he make when he made these calculations?
In a nutshell, we'll come to that in a moment now. But
So the theory that you're talking about, what you're talking about is that that there is a decrease in energy of the wave due to dissipation as it travels through the universe. There's an attenuation of the wave, which people have called tired light. Now, in the past, the theory has been that there's no mechanism to cause this tired light
yeah,
because the mechanism that would cause the tired light would cause the wave, the spectral lines to smear out. And since no smearing out is observed, therefore there is no tired light. That's the mainstream position. Your
yeah.
theory wouldn't cause the spectral lines to smear out. Which is the main reason that your theory would be um, acceptable to the mainstream, I think.
Well, it's waves versus photons too.
Well, the traditional tired light assumes photons, and they hit electrons in the intergalactic medium, and that scattering is what causes the tired light. And they say that mechanism, if it explained the redshift, would cause spectral lines to spread out, and that's not observed.
Okay, my question is about blue shifted galaxies. How to explain on base of tight light? Even
Well,
Andromeda, the closest galaxy to us, blue shifted. We have
well,
thousands and thousands blue shifted galaxies. What are we talking about?
well, my next slide adverts to that. It doesn't actually answer your question, so you might want to come back, Vladimir. But my next slide is talking historically
Let's
about that.
continue, guys.
Shall I
Let's see the
continue? Yeah.
whole picture.
I've got another couple of slides.
Yes, yes.
Okay. Now, what's happening now? Why isn't this? Sometimes it doesn't go on.
We see it here.
Yeah, okay. You see my next slide.
Hubble versus Maxwell laws,
Yeah.
yes.
So I just want to say a bit about Hubble versus Maxwell, and I want to refer to Slipher and Lemaitre as well. Well, the current expression of this linearity between the distance to a galaxy or a nebula, as they would call them in the past, um, would be that Z is the redshift there in terms of wavelength change over original. C naught again is the speed of light without any refractive index, and H naught is the Hubble constant. Now, so there's a linearity. Well, if you write out the Doppler equations, whether in relativistic form or in classical form, uh, and you say that V is very much less than C, so V over C is less than 1. Well, then Z is approximately equal to V over C. It reduces to that. It's just using the binomial theorem where you have something like 1 plus x to the power of n, where x is very much smaller than 1. Well, the value is approximately 1 plus nx. And from that, you get that the distance to the object is proportional to the speed of recession, speed, and H naught is the Hubble constant. Now, however, really that came first, and I must attribute that or blame, depending upon which word you wish to use, to Werner Slipher beforehand, because what he was doing, he was observing spectroscopically these distant nebulae, as he called them. They didn't really know what they were in those days. Around 1912. And actually, the first nebula was the closest one, what Vladimir referred to, Andromeda. And he found there was a blue shift. And he got into his mind that it was Doppler straight away. That meant it was moving towards us at a speed. So then he started looking at all these other distant nebulae, didn't know what they were. And he found that the vast majority of them were redshifted. So without even thinking, he said it's a Doppler shift. And he used that equation there because V was very much less than C. And he got that equation. So in a way, it's a Slipher's law in a way. But and then later on, we went back to the more fundamental position whereby we got rid of the velocity and just found, well, you see, as you know, Hubble started looking at the distances. You see, Slipher didn't know what the distance was at all, and he was convinced that it was a velocity, it was a Doppler effect. So, but Hubble started looking and cataloging all these nebulae, and he found that actually they were very much further away than had been previously thought. They weren't part of the Milky Way galaxy. They were separate galaxies. And he used the results of the Leavitt, what was it, Henrietta Leavitt, on the Cepheid, I think that's the way you pronounce it, the Cepheid variables. And he actually did use a little supernova information as well to calculate the distances, because you knew what the brightness was, the absolute brightness, and therefore you got distances, and you got this value. But actually, so Lemaitre, of course, before that, just a couple of years before, maybe 1927 or something, had postulated the whole conception of the expanding universe and the Big Bang and all that. So I think actually in 2018, the International Astronomical Union propositioned its members as to whether they should not rename this law here, or perhaps this one. Maybe this one is normally in terms of velocity now, the Hubble-Lemaitre law. And I think the majority of people acceded to that. So I think maybe it might be known as the Hubble-Lemaitre law. But anyway, for shorthand, I'm calling it Hubble because Hubble got the distance But Hubble wasn't convinced, contrary to what you'll read in all the textbooks. He wasn't convinced that it was a Doppler effect. He said that's one explanation, and Slipher was convinced of that. He wasn't willing to entertain another view. But he said it could be tired light. He didn't dismiss it. There could be other reasons. We don't know. Now, I just point out that if you take this simple linear law, it's unbounded. So as Z approaches, I didn't want to do that yet. That's a surprise. As Z approaches infinity, the rate of change uh,
Hello.
yeah, the rate of change is not zero. It keeps on going up to infinity. The rate of change is a constant, C naught over H naught. Now, well, I'll come back to that in a second. With the Maxwell, just by fiddling around with the exponential term, you get that. And the rate, it's bounded. So as it goes to infinity, it tails off. Now, to stop this thing going up to infinity, what they do, and I've only put it down just for your information, gentlemen, but I haven't seen calculations of it. They use the Friedmann equation, because remember, Friedmann had done the analytical work with regard to the expanding universe from Einstein's general relativity equations. And for large V over C, an integration. It's a bit of a fudge factor, I would say. It's an integration over Z, with respect to Z, of divided by H, which is a factor, a function of, it's a complicated function, the energy density of the universe, the curvature of space, and the cosmological constant, or dark matter. So all I'm saying is the mainstream will say, oh, we have an equation which will tail off. But I'd like to see more results of that. I'll be showing you the graphs in a moment. And I have referred in the past, I'm blaming Slipher. It's not to be taken that I'm critical. He was a very great astronomer. He did a lot of very great spectroscopic work. He did it in Lowell Observatory, and a very eminent man. But he convinced himself from I would say from observing the blue shift of the Andromeda galaxy that they are all Doppler shifts, and that is a logical fallacy. It's called Bob will know all about this, consequentum affirmans, which is affirming the consequent. So in other words, given that A always implies B, then B always implies A. So if A is the recession of the emitting object from observer, and B is spectral redshift. So if there's a recession of the emitting object, you will always get a spectral redshift. But that doesn't mean if you have always a spectral redshift, it means recession. There could be other reasons for it.
I haven't heard you mention Halton Arp's intrinsic
Yeah,
redshift.
yeah, you talk about that a lot, and it's a good point. Maybe I think it's worth bringing up, Rick, and it certainly throws doubt on this universal Doppler redshift.
Is
But
an
in a
is
way,
Andromeda actually moving towards us, or is
well,
it just
that's a good point.
an old galaxy?
There
Yeah,
can be more than one mechanism. It could be
And
that's
I
Doppler.
true.
was just
Yeah,
going to say it could be Doppler, it could be tired light, and a combination of all three. Arp's
and that could
intrinsic
be true.
redshift.
Yeah, that could be true in all of these cases. And again, I may be having to take a bit of support from my hypotheses non fingo. uh, I'm not sure. I don't know if we have enough data yet, really.
Well, the point is that the only data we have is redshift versus distance. There's no direct evidence of expansion.
Yeah,
Well, Arp
and
Arp has his quasars that are physically attached to galaxies that are redshifted, but they're less redshifted than the
so,
quasar that's physically attached to it.
so that's throwing another question mark into this whole situation. You see, to me, the Andromeda thing is just, well, I know Vladimir says there are many of these, but it's a bit of an anomaly. Since you have the vast majority of these observations show redshift, well, then if you put a question like this in, that there must be dissipation because of what the equations say, if you put in a question mark in this to say, here's something which we know is nearer, but it has the same redshift, Holton ARP, you're questioning all the data. It's just too good to be true that you have all the data and they're all caused by this expansion. And by the way, Slipher had no conception of an expanding universe. He said these are objects physically traveling away from us. Now, the modern astronomers, as far as I can gather, will not express it in that way. They'll say this isn't simple moving away. It's the expanding universe. The whole universe is, and that's what's doing it. That's what they say.
It's because it fits with GR.
That's right. That's right. And that's what this equation does as well. This is based on GR, and they're quoting this every day. That's right, Jim. So, so if you like, I can come. Let me say, I can come to the next slide, which is the graph. I had to put that in to be fair to them because they say, oh, GR satisfies it all here. But I'd like to see that equation. That's a very complicated function, which would have to be evaluated for all values of Z. And anyway, let's take the linear law and we'll take Z. We'll concentrate on Z being. I'll plot it up to a value of 4, say, but it has to be much less than 0. Sorry, much less than 1 for this approximation to apply. So anyway, I've plotted it up to 4, the value of 4, but and I've normalized it to this RD, this factor, because remember I said that it dissipates by a ratio of E/1 after 10 to the 10 light years. Now, I've also plotted, decades ago, they thought the Hubble parameter was something like 50 kilometers per second per megaparsec. Nowadays, they say it's about 70. But it doesn't really make much difference. I've plotted that, you get that linear thing. Now, if you plot this equation, which I'm calling the Maxwell equation, because it's retaining the conductivity term, it's solving differential equations, and it's getting the exponential dissipation factor in exactly the same way as Rayleigh did with the sound. You get this curve, which is a more realistic curve. And actually, I think in the very early days, there were values of Hubble parameter 600, and it would appear to me that all curves are linear within a very small area, so they were maybe dealing with this area here and it's almost linear, but you could actually get a much better fit by having a much higher Hubble parameter there. So it's a bad fit. You're getting quite different values here.
Does the Maxwell red curve get to a asymptote as the wavelength increases? Or does it keep going up forever?
No, it's asymptotic
Going to put
to
on the
this.
piece of work
Remember,
that was thrown across the floor.
what's that
I
noise?
almost stepped on it for good measure.
Is that your wife? There's one's cable.
Well, with lambda CDM, they scale it so it ends at 13.8 gigayears.
Well, no, this thing approaches it parallel there. It's asymptotic to this axis to the infinite distance as far as you go away. It never goes right up to infinity, but it's asymptotic. Actually, I thought actually it'd be actual value were asymptotic too, but I've differentiated that function and just seen what happened when Z approached infinity, and I got 0. So it means the rate of change is 0, but
Okay, thank you.
okay. Anyway, that part there. Anyway, it is asymptotic. I just wasn't quite sure. So, they might say, look, you've been unfair. Our linear law will only apply for small, certainly much less than 1, because you see they say, according to general relativity, that when Z exceeds 1, the recession exceeds the speed of light. And they say, I'm saying they all the time, that it doesn't contradict special relativity because you're in a general relativistic world in which there's expansion occurring. So it's only an apparent, I don't know, they're talking in riddles as far as I'm concerned, but it's only an apparent. But anyway, they say, look, you better consider these values here. But I'd say, well, look, the Maxwell curve is still very much less than this one. Take the 70. And remember now, and will be my last slide. I've only one more slide to come. Uh, there is a tension in agreeing what the values of Hubble parameter are, depending upon which way they're calculated. And that throws great doubt on the veracity of the whole system. We should have consistency in the values here.
Ian, if I may ask you, sir, you say great doubt. To me, it looks like this completely excludes it.
Well, yes, I don't think that's going too far, Jim. You're maybe a bit more of a direct speaker than I am. I don't disagree with you.
Okay, thank you. That's
So
all.
yeah, maybe in the
I was checking if I was really understanding what you're saying, because if we're going receding at the speed greater than the speed of light, I would think that would exclude the whole theory, the whole package, as you've shown today.
yeah, yeah. You're thinking in terms of material objects, I suppose, Jim. But yeah. Well, anyway, I have some of these summaries in my last slide, which is coming now. Perhaps I'll come to it, and I just have about three conclusions, and they're just what you were saying there, including what you've just said, Jim. So maybe
Thank you.
I might just say that I do confess that they have this very complex equation here, Friedman, and I'd like to see maybe a paper where they evaluate that for various values of z, where they're claiming that the speed is exceeding the speed of light, and I'd like to see whether what happens. They say that whether it actually goes like that, or I have never seen that. I'd like to see how that they would say that's the correct curve because they say the Hubble
Well,
curve is about 70.
I think a lot of this is complicated by the fact that now you have inflation and you have dark matter and dark energy. And those are additional parameters that have to be taken into account in their mainstream understanding of what's going on.
Right.
And
And Harry, have you heard of phantom energy?
no, I haven't heard of that
Okay.
one yet.
Well, I came across that just the other day, rehearsing for this talk today, and I've even forgotten exactly what it is, but it's an extrapolation of dark energy or something. You could look it up, but and many of the cosmologists say they don't believe in it, but it's another one. So you're
Have you
you're
heard of
doing right.
Have you heard of phantom limbs?
Phantom lens.
Limbs,
Oh,
like
limbs. Yeah,
like
yeah.
arms and legs. When people have their arm
Right.
removed for some
Oh, yeah.
reason,
They
they
feel it
they
still.
feel
Yeah,
it's still there. Yeah.
yeah. Quite so. Yes. Yeah. Well,
Okay,
it's
so
fallen
can
in
we move?
mind.
Can we
Yeah.
get to your
This
conclusions?
is the conclusions now. I say the physical properties of the medium for electromagnetic propagation correspond one-to-one for fluid media carrying other waves and are governed by the same equations, which I've given you at length. I haven't to solve them. It'll take a few pages of mathematics, but I've given you the equations. And if you want the
This
solution,
is a conclusion that the mainstream avoids.
yeah. And the one-liner, I think, as to why they avoid it is because EM doesn't have a medium of transmission. I don't know why else they said it's different.
Well, that would be one view of it. But I think as far as cosmology is concerned, which is what you're referring to, their medium is the space-time medium of general relativity.
which
Yes.
isn't a medium.
They've reified it to make it to be the medium of the universe.
But it's just math. It's just numbers.
Correct.
See,
Correct. It's just
Einstein
math.
himself even called it a type of ether in 1920, but
Right.
they don't give any properties of it or anything like that.
Well, the properties are the space-time.
Yeah.
I say
Okay, well,
it
that's
is dark.
curved
It's no
space-time.
space-time in general relativity. Guys, when we will stop this bullshit? There is
Well,
co-manifold. There is no time in general relativity at all. It's geometry only. Jim, I'm absolutely right with you. It's mathematics only. There is no correlation to physics at all. Complex time in his model, it's bullshit. We
Well,
live in
well,
a real time with you
perhaps I
guys.
better deal with the other two because we're running out of time, and if there's time we can follow. My
Geometry,
second
that's
point,
it. Simple like
is that
this.
okay? Yeah. Treating, maybe I'm following on a bit, treating EM radiation analogously to other waves leads to a more rational description of phenomena, in particular redshift data and causal explanation. A bit like Einstein's idea of length contraction or time dilation. What are the no causes? They're just mathematical, as Vladimir is saying. What's the causal explanation of redshift? Oh, we don't know. The universe, there's a big bang or something. And then my last point is if, and this has got back to what we discussed a moment ago, if the so-called Hubble redshift linear law is incorrect, we should expect incorrect. We should expect discrepancies in measuring the proportionality constant by supernova. This is supernova 1A, where you use them to these particular types of white dwarfs, and the Cepheid distance
Cepheid.
estimate. No, I looked up the pronunciation of that. It's Cepheid.
Oh,
Yeah, I used to pronounce it Cepheid as well. Anyway, what's in a word arose by an
well,
end.
I've heard a lot of cosmologists pronounce it Cepheid.
Yeah. Okay. Well, I'm using dictionaries, but anyway, we'll have to come back to that if necessary. I bet I'm continuing.
It
And
does
I
make
was
a
going to,
difference how to pronounce.
what
Sorry.
do you, how do you pronounce it?
Continue.
It doesn't matter. It's only an argument. Anyway, I'll continue to pronounce it the way the dictionary said. Cepheid. It comes from Cepheus, by the way. It's the constellation in which they were first discovered. But anyway, distance estimation versus, that's one way they do it by finding out the way Hubble did, basically, by modern techniques, and versus the cosmic maker of background early universe ascertainment. So assuming their theories are correct and the universe is 3.7 thousand million years old and the way it could evolve and the expansion and so on, you get a different value. They're not very different between 67 in the latter case and 70 plus in the up to 73 maybe in the former case. But I say this Hubble tension, which actually is a euphemism, is itself a discountenance of existing theory of expansion. If there were nothing else in our arsenal, we might be suspicious of the current existing theory of expansion of the universe because of the Hubble tension. So they've
If it
shot
is,
themselves in the foot. So that's my last word for the moment. There may be a moment or two to
if it
discuss.
really is 73, then that implies the universe is only 12 billion years old.
Yeah, yeah. And the only unfortunate thing is we'll have to change the parameter now as the telescopes get more powerful. Of course, they talk about a Hubble constant, but that's a misnomer. Even taking, the conventional view, it's a function of time. So obviously, it's decreasing with time
And
over long periods of time.
it ends at the Big Bang event.
Yeah, presumably so. Yeah, yeah.
And
Where's up?
latest deep field from JWS showing objects of redshifts of around 28, 25 to 30. How fast are those suckers moving away from us? 2, 3, 4 times the speed of light?
Yeah,
That's
that's what the
ridiculous.
conventional people would be forced to say. Yeah.
And
The extent of the universe is unknowable with our current technology, is what I'm thinking.
Yeah.
well,
Well,
there's a lot of evidence that that with the Tolman brightness test and just the angular size of these new galaxies is much more consistent with a non-expanding universe.
sorry, what did you say there? Tolman evidence, Jim?
The surface brightness of very deep galaxies.
Oh, yes, yes.
Fits the non-expanding model much better.
Yeah, well, that's similar to what I said as well.
Yeah.
Well, I mean, I lay my cards on the table from my point of view, and I don't have all the data. A bit again, my not framing hypotheses. I don't accept expanding universe. I don't expect any of that. To me, I work on the premise that the universe is infinite. It has no bounds, and it always has existed, in both in time and space. That's what I'm doing at the moment, anyway, in my analysis.
Well, today's
Well,
presentation, I draw two conclusions from it. One is that Harry Richter's sessions might be the best discussions of key issues in science on the internet today. And the second conclusion is that the most popular theories today are the ones that are the least supported by actual evidence. If there's evidence supporting the theory, it is rejected. If the theory contradicts evidence, it is very popular. That's the second conclusion that I draw.
Conspiracy
Feynman
much
said that
there,
as well.
James?
Feynman said, "Look, if it doesn't fit the facts, just drop it." But no, they're not complying with that edict.
uh, okay. Uh, all right. Does anybody have a rebuttal of or or something else to add to what Jim just said?
Even a comment.
Okay.
Guys,
Look, I'm a
okay.
bit enthusiastic because you've given me some support, and I'm happy to have criticism as well. If you'd like to look into anything and come back to me, but it gives me some idea to further my ideas in this area, and there
The-
might be some interest.
Does the dependence on frequency of the dissipation or whatever, it's not really dissipation, right? I mean, one of the supposed facts of cosmological redshift is that it's independent of the the frequency of the spectral line.
Well, he showed that it did in the case of waves in air, but I don't think he made that point with respect to EM radiation.
I think he said something about EM, the wave interacting with an electron in its motion through the universe,
Who is
making
he?
it more tired. Ian,
Ian.
Really?
Okay, let's let Ian. The question, Ian,
What
is
is it?
if your theory is correct, wouldn't that mean that there would be different redshifts for different frequencies from the same galaxy? So that would mean that the redshift, like at radio waves, would be different than the redshift for light waves because of the frequency difference. But I
Good
think
question.
I
Yeah.
think you're assuming there is no frequency difference for EM waves, as you showed for waves in air.
Well, to get some evidence for that cosmologically, Harry, you'd need to have an object in the same part of the sky, same distance away, and so on, emanating from which light has emanated at different frequencies, and you could have to compare how they're attenuated. If one is attenuated more than the other.
Right. That's what I'm saying. That I'm not really sure that there would be for, like, for instance, a visible spectrum. I'm not sure there'd be enough of a difference to be detectable. Um, but if, like, say, for instance, you were to compare radio waves with light waves, then there might be a difference detectable if there was a dependence of attenuation for frequency.
Well, could be where part of Vladimir's work on radio bursts, fast radio bursts or something, could be compared with visual results, and one could maybe establish that. I suppose if one did establish the same frequency variation that I talked about, that would be an added reason to believe the theory is correct. But I suppose if there weren't that, you'd have to put a big question mark around.
Unfortunately, these fast radio bursts don't show up in the visible, do they, Vladimir? I don't.
No, guys, it's so far away. You can take a look only with radio telescope. That's it, simple like this. But what is important, there is a dispersion of these radio waves, means there is some variation in speed of electromagnetic waves. Guys, let me do a few comments about, because it's not so much time left, but I want to tell you what the problem is with the existing model. The problem is singularity, and all this behavior around in the world depends on the very first singular momentum, the T0 time. The second point is practically infinite universe. Then we have the z equals more than one, less than one. Who cares? Let me tell you, in my model, there is no red shift, blue shift at all. It's a bullshit of our behavior, of our investigation, of our test results. Why? Many times I told you analogy. We have our planets around sun. Sometimes planet moves, Mars moving to get together toward to the Earth. Another time in 2 years, 3 years, it's moving outside. What the redshift of Mars against our Earth? What is the redshift? There is no meaning at all. That's why the same story in my model with supercluster. Supercluster, it's an analog of solar system. And all these galaxies, they can move toward us, to our galaxy, the outside of our galaxy. We don't know. Everything depends on the behavior inside of the supercluster. That's why there is no mean for redshift, blue shift at all. It's only some result of movement of these galaxies against each other in superclusters. That's it. The next point, there is no expansion of our space, whatever. There is stretching of our cosmic medium. Stretching. We have our world finite. There is no problem with infinity. And finite stretching speed is electrodynamic and gravitodynamic constant c. It is not speed of light. Guys, many times I told you the difference. There is no speed of light in electromagnetic waves. There is no speed of light
Right.
in any place. That's why, guys, we live in a finite world as a patchwork quilt. Many times I told
All
you,
right. Okay.
many.
Vladimir, we got 3 minutes here. Do you want to
Okay,
finish up, Ian?
That's why, and what is important, don't ask the question, there is a cosmic medium or not. Microwave background radiation, fine infrared background radiation, gamma radiation, all this background and intergalactic plasma. We don't ask even, there is a vacuum or not. There is none.
All right. All right. Let's let Ian, you having some fine? We got like 2 minutes.
Okay, I'll be very quick. All I can say is thank you very much for your attention and for all your questions. They certainly helped me in spurring my mind to new ideas. And I'm actually surprised that nobody really has gone into much detail on this analog business because, the same mathematical theories.
You mean the analog of wave behavior in different mediums?
Yes. And questioned, therefore, the general conception of electromagnetic radiation, which is dealt with in quite a separate way. And I've just considered that they're so similar that they must be more to it than meets the eye, literally, actually, in this case.
All right, I'd like to close out because before we get interrupted, okay, so we want to mention that we don't have anybody scheduled to present after the next meeting. So if you're interested in giving a presentation, let me know. So we need people to give talks. I want to thank Ian for his presentation today. And I guess my summary comment would be mainstream's assumption is that the universe is essentially not a physical object. It's a mathematical object defined by the geometry of general relativity. And that, from their point of view, that's what the medium is. And so all of their theory of cosmology is based on the assumption that the universe is a space-time object, not a physical object, and so therefore there's no real place for your theory in it, Ian.
It's been all explained by space-time, yes.
Regardless, it was a good talk anyway, Ian.
Well, thank you very much anyway. I hope I got you thinking, if nothing else. You don't have to agree with
Sorry, I
everything.
missed the beginning of your talk today. I'm very sorry. It was not my mistake. I'm
No,
sorry.
that's fine. But Roger has been recording it all, so you can look back.
Okay,
Come back
okay.
to me if you have any
I
problems.
missed
Any
it.
of you.
I'm sorry.
It'll be
Yeah,
on
great.
the recording. I have
Great.
it recorded and Roger's. Okay, we should be stopping here.
I'll not